In the world of military aviation, to be seen is to be vulnerable. For decades, pilots and their machines engaged in a deadly dance-speed altitude. The goal was simple: fly faster, higher than the enemy's defenses. But a new idea emerged from the shadows of the Cold War. It was a revolutionary concept. What if an aircraft could be made invisible? Not to the human eye, but to the electronic eyes of radar that guarded the skies. This is the core idea of stealth. It is not true invisibility like something from a science fiction story. Instead, it is the art and science of drastically reducing an aircraft's signature, making it incredibly difficult for an enemy to detect, track, and attack. Stealth technology represents a fundamental shift in military thinking. It changed the equation of air power forever. It can slip through the most advanced air defense networks like a ghost. The contest to invent and perfect this invisible aircraft became one of the most secret and intense technological races of the 20th century. It required brilliant minds to rethink the very basics of aircraft design. This essay will explore the fascinating story of stealth aircraft. We will see how designers and scientists developed the key technologies and meet the iconic aircraft that brought stealth from theory to reality. To understand stealth, one must first understand radar. The word radar is an acronym. It stands for radio detection and ranging. A radar system sends out a pulse of radio energy from a transmitter. If it hits an object like an airplane, some of that energy bounces off and reflects back. By measuring the time it takes for the echo to return, the system can calculate the distance to the object. For military forces, radar was a game changer. It was first used effectively in World War II. It allowed defenders to see incoming enemy bombers from hundreds of miles away. This gave them precious time to scramble their own fighter planes to intercept the threat. After the war, radar technology became much more sophisticated. Ground-based radar networks, connected to surface-to-air missiles, created deadly no-fly zones. The problem for conventional aircraft is their shape and material. Metal is an excellent reflector of radio waves. Rounded fuselages, large vertical tails, exposed engine inlets. This creates a strong radar return or blip on the operator's screen. A large bomber might have an RCS the size of a barn. A smaller fighter might be the size of a car. The goal of stealth technology, therefore, is to reduce an aircraft's RCS to an absolute minimum. If a large bomber can be made to have the RCS of a small insect, it effectively becomes invisible to the enemy's air defense system. The quest for stealth did not begin with the famous Nighthawk or B-2 bomber. Its roots go back much further, to the early days of the Cold War. The famous U-2 spy plane, for example, flew at extremely high altitudes. But on May 1, 1960, a U-2 piloted by Francis Gary Powers was shot down by a Soviet surface-to-air missile. This event proved that flying high was no longer enough. One of the earliest attempts to reduce an aircraft's visibility to radar was a project called Kempster. Engineers developed special coatings panels made of ferret-other materials designed to soak up radar energy like a sponge. While these modifications did reduce the U-2's radar cross-section, the reduction was not dramatic enough. It showed that simply adding materials to an existing design was not the answer. Stealth had to be designed into the aircraft from the very beginning. The next major step came with the development of the SR-71 Blackbird. This was an aircraft built for pure speed and altitude, but its designers at Lockheed's legendary Skunk Works also incorporated early stealth features into its design. The SR-71 had a unique shape with blended wings and fuselage known as chines that helped to scatter radar waves away from the source. It was also painted with a special black paint that contained tiny iron spheres. While the SR-71 was not a true stealth aircraft by modern standards, it was a vital stepping stone. Incredible speed, high altitude, and reduced radar signature made it nearly impossible to shoot down during its long operational career. No SR-71 was ever lost to enemy fire. The true breakthrough in stealth came from a place of pure theory. In the mid-1970s, a physicist at Lockheed's Skunk Works Denys Overholzer discovered an obscure paper by Soviet mathematician Pyotr Ufimtsev. Ufimtsev's equations showed how to calculate radar cross-section of a two-dimensional shape. Most American engineers dismissed the paper, but Skunk Works saw hidden potential. They envisioned a computer program based on the equations to design an aircraft of flat panels, facets. Angle the facets to deflect radar waves away from the receiver. Revolutionary, because aviation had always favored smooth, rounded aerodynamics. Skunk Works' concept Have Blue proposed the opposite, nicknamed the Hopeless Diamond by engineers. But their computer model, Echo 1, predicted near invisibility to radar. The Defense Advanced Research Projects Agency DARPA secretly funded two Have-Blue prototypes, small, single-pilot demonstrators built in secrecy at Skunk Works in Burbank, disassembled and loaded into a transport plane flown to a remote test site in the Nevada Desert Groom Lake Area 51. The first flight, December 1977. Against all odds, the Hopeless Diamond flew. Tests were a stunning success. Flying toward a radar range, operators saw nothing. A chase plane had to confirm the aircraft was still there because radar operators could not see it. Have-Blue proved the faceted shape worked. An aircraft could be made thousands of times less visible to radar than a conventional plane. The era of operational stealth had begun. Shaping an aircraft to deflect radar waves was only one half of the stealth equation. The other, equally important part was the development of materials that could absorb radar energy. The idea wasn't entirely new. In World War II, the German Navy coated submarine snorkels with a rubbery, carbon-filled material to hide from radar. But scaling RAM to a high-performance aircraft was far harder. Early stealth jets like the F-117 used multiple RAM types. The main body was covered in a flexible, rubber-like sheet loaded with tiny ferrite particles, iron compounds that absorb radar. It worked, but it was heavy, hard to apply, and demanded constant maintenance. Leading edges, the wings and the tail surfaces, were natural radar reflectors. Engineers built composite structural parts with absorbing properties baked in. The cockpit canopy was another trouble spot. The fix, a very thin, transparent conductive coating like gold or indium tin oxide. Modern fighters like the F-22 and the F-35 now use baked-in structural stealth. Instead of heavy surface coatings, absorbing properties live inside the composites. Result, aircraft that are lighter, more durable, and less maintenance-dependent. The Magic Skin is a complex, multi-layered system, a crucial partner to shape in the quest for invisibility. The success of the Have-Blue program led directly to the first operational stealth aircraft, the F-117 Nighthawk. Despite its F designation for fighter, the F-117 was purely a ground attack aircraft, a stealth bomber really. Developed in total secrecy, its existence wasn't officially acknowledged by the U.S. Air Force until 1988. It was a strange, angular black jet that flew mostly at night. Its mission? Slip undetected through enemy air defenses and destroy high-value targets with laser-guided bombs. While the F-117 was a tactical aircraft, the next step was a strategic long-range stealth bomber. This led to the creation of the B-2 Spirit. Developed by Northrop, the B-2 used smooth, continuous curves instead of sharp facets. The flying wing design has no tail surfaces. It can fly over 6,000 miles without refueling, carrying a massive payload of conventional weapons or nuclear weapons. Its purpose, hold any target on Earth at risk, able to penetrate even the most heavily defended airspace you can imagine. The next generation combined invisibility with high-performance fighter capabilities, resulting in the F-22 Raptor, an air superiority fighter. The F-22 is stealthy, incredibly fast, highly maneuverable, and super aware of its surroundings thanks to advanced sensors. Its mission is to clear the skies of enemy aircraft, protecting less stealthy planes. The F-22's mix of stealth, speed, and advanced avionics made it the world's most dominant fighter. Following the F-22 came the F-35 Lightning II. Designed to be more versatile and affordable, it's produced in large numbers for the U.S. Air Force, Navy, Marine Corps, and allied nations. While not as stealthy or as dominant in air-to-air combat as the F-22, the F-35 is a true multi-role jet. It excels at ground attack, intelligence gathering, and electronic warfare. Its strongest asset is a network of sensors, gathering battlefield information and sharing it across the force. The F-35 acts like a quarterback in the sky, amplifying the whole force. These aircraft, from the F-117 to the F-35, represent the evolution of stealth, from secret experiment to the cornerstone of modern air power. For years, stealth technology existed only in the shadows, a secret capability known to just a select few. But all that changed on the first night of Operation Desert Storm, January 1991. Before the main wave of conventional bombers and fighters crossed into Iraq, a small group of F-117 Nighthawks slipped across the border, completely undetected. Flying right through the heart of Baghdad's defenses, the F-117 pilots dropped their laser-guided bombs with pinpoint precision. They destroyed critical command and control centers, they destroyed communication hubs, they destroyed key radar installations. The Iraqi defenders were, well, blind and deaf. By the time the main wave of non-stealthy aircraft arrived, the air defense system was in chaos. The F-117S had kicked down the door. During the entire conflict, F-117S flew nearly 1,300 sorties. They attacked some of the most heavily defended targets in Iraq and scored a remarkable number of direct hits. Not a single F-117 was lost or even damaged by enemy fire. The age of stealth warfare had arrived. 8 years later, during the NATO air campaign over Serbia and Kosovo in 1999, stealth aircraft were called upon once again. This conflict, though, also gave us the first and only combat loss of an F-117. On March 27, 1999, an F-117 was shot down by a Serbian SA-3 missile battery. The Serbian forces used clever tactics, like operating their radars for very short periods and using older long-wave radars that were just a bit better at detecting the F-117's shape. The shoot-down was a shock, but it also served as a valuable lesson. Stealth is not a cloak of absolute invisibility. It's a massive reduction in detectability that must be combined with smart mission planning and tactics. The B-2 Spirit bomber first saw combat in that same conflict over Kosovo. Flying non-stop from their base in Missouri, the B-2S would fly a 30-hour round-trip mission to strike high-value targets in Serbia before heading all the way back to the United States. This really demonstrated the incredible global reach of the stealth bomber. These missions proved just how effective stealth technology could be. They showed that a small number of stealth aircraft could achieve results that would have previously required a massive force and would have come at a much higher cost in aircraft and lives. For many years, the United States held a near monopoly on operational stealth technology, but this situation was never going to last forever. Other major world powers, especially Russia and China, understood the revolutionary impact of stealth and began their own secret programs. The global race for invisibility had begun. China has made particularly rapid progress. In 2011, it surprised the world by flying its first stealth fighter prototype, the Chengdu J-20 Mighty Dragon. Russia, with its long history of advanced aircraft design, has also been developing its own stealth fighter, the Sukhoi Su-57 Felon. This global spread of stealth technology is changing the strategic landscape. The days of a U.S. stealth monopoly are over. The next great leap in stealth aviation will almost certainly involve unmanned aerial vehicles or drones. Removing the pilot from the aircraft really opens up entirely new design possibilities. Without the need for a cockpit, life support systems, or the physical limitations of a human body, a stealth drone can be made smaller, lighter, and more perfectly optimized. Future stealthy platforms will need to manage their entire signature, reduce heat signature to evade infrared sensors, use advanced electronic warfare to jam and deceive enemy sensors. Stealth will become a multi-layered approach of design, materials, and electronics. The future of air combat will be a complex cat-and-mouse game between stealth and counter-stealth. It'll be a battle fought not just with missiles and guns, but with processing power, algorithms, and control of the electromagnetic spectrum. Can a network of advanced sensors defeat a perfectly shaped stealth aircraft? Can a new generation of stealth drones operate with enough intelligence to outsmart human defenders? These are the questions that engineers and military strategists are wrestling with today. The secret contest to invent the invisible aircraft, which began in the deserts of Nevada decades ago, continues in laboratories and on computer screens around the world, pushing the boundaries of what's possible. Thanks for being with us. Keep watching, keep learning. See you guys in next video.